Fantastic. All right. So yeah, today I'm going to be giving you a bit of an introduction to RSA. I know a lot of you are already familiar with RSA, so I'm also hoping to cover a few of the sort of more esoteric elements of doing representational similarity analysis. But for those of you who are unfamiliar, representational similarity analysis is an approach that compares what are called, in fancy lingo, second-order isomorphisms, or more simply, similarities between different measures. So rather than building a model which directly relates one measure to another, we first compute the similarity of different stimuli or objects in a very generic sense in one measure and in the other measure, and then relate those similarities to each other. And this was an approach, although it has some precursors in earlier work, that in neuroscience was formulated by Kriegeskorte and company to basically link together different approaches to measuring brain and behavior. It can be very difficult to try and build a model which directly relates, for example, single unit recordings in an animal brain to fMRI signal in a human brain, to behavior, to a computational model. And by reformulating all of the outputs of those things in terms of the similarities between whatever the things are that you want to consider, the objects that you're analyzing, it becomes a lot easier to then relate them together. So it's a way of sort of spanning, as this diagram illustrates, different branches of cognitive neuroscience. And the first question that I think we should consider is, how do we even measure similarity? The similarity between two different sort of data objects, data vectors, can be measured in a lot of different ways. There are dozens of similarity measures, actually. However, if we look at sort of the history of how our studies have actually been done in cognitive neuroscience, there are really only sort of three big measures: the mean distance, correlation distance, and Euclidean distance. So I'm first going to take you through these three distance metrics to understand how they're similar and different to each other, how they're related to each other, and a consideration of when we should use each one of them. So for those of you who want to follow along with me in R, you can see the R code blocks embedded in the text. This is an R notebook, so it's similar in concept to a Jupyter notebook, but it's implemented through RStudio. So if you have R and RStudio downloaded, you can execute this at the same time and build up this notebook. If you don't care about doing that, you can either follow along on the screen, or there's an HTML precompiled within the GitHub repository that you can just look at in your own browser. And if people are not familiar with any of the R syntax, I'm happy to explain exactly what's happening there. If you care to sort of not care about that level of detail, that's also fine. So what we're doing here simply is actually just generating some random data. Very, very simply generating 4 different data objects, each consisting of 200 data points. So you can see the 4 of these plotted out here, conditions 1 through 4. We've sort of linked them together, but there's no like autocorrelation in this sequence. And you can see they have slightly different statistical properties. In particular, the correlations between them, so that when one goes up, the other goes up or not. And the means are also shifted from each other a little bit. And we're going to look at how these sequences are similar or different using these different distance metrics. To begin with, we'll talk about mean distance. This is effectively what we're modeling when we use the GLM and do a contrast. So this is like a univariate analysis. You can think about it in the RSA framework too. This is effectively like taking an ROI, computing the means of your conditions, and then just taking the absolute differences between those means as the similarity or distance between your conditions. So in this case, if we look at our 4 nominal conditions in our data set, we can see that they have pretty markedly different means. So 2 of them have means that are right around 0, and 2 of them have means that are right around 1. And if we think about the distance between these as simply the difference in the means, then we end up with a similarity matrix that looks like this, where high values indicate greater similarity and low values indicate greater dissimilarity. So you can see that these conditions are really, oh sorry, that's actually the other way around. The low values indicate low distance and high values indicate high distance. So conditions 1 and 2 are very close to each other, hence why there's very little distance between them. They're highly similar. And then conditions 3 and 4 are very different from conditions 1 and 2 because the means are higher. And so these are quite different. So again, this is effectively just sort of the traditional univariate contrast approach formulated in terms of the similarity between different conditions. we can compare that with Euclidean distance, which you can see here. The Euclidean distance is just the sort of everyday distance we talk about. Usually that's three-dimensional. So the distance between me and the back of the classroom is in a three-dimensional space, really more of a two-dimensional space since depth doesn't really come into it. And we can do that with an n-dimensional space, in this case a 200-dimensional space, which is our data pattern space. Simply by taking Euclidean distances. This is basically the sort of sum squared difference like the Pythagorean theorem would suggest. And in this approach, you can see that we get a really different pattern of which conditions are similar and which ones are different to each other. So you can see that there's a lot of similarity along the diagonal. That's always going to be the case. Everything's always very similar to itself. But off the diagonal, things are very different from each other. But there's a little bit of additional structure here such that this sort of like counter-diagonal is particularly distant. And we'll see why that is in just a second. So the final distance we're going to talk about, and this is actually the most popular in representational similarity analysis, correlation distance. So this is literally just sort of 1 minus the correlation coefficient, so if it's a Spearman or Pearson correlation. You can see in the scatter plots here what the correlations look like. And you can see that certain conditions, regardless of their means, are correlated with one another. So it's a property of correlation that it discards the mean of a data set. Basically, you z-score data before you put it into a correlation effectively. So we can see correlations between conditions 2 and conditions 4 and conditions 1 and conditions 3. So although these have quite different means from each other, as we saw a moment ago, these means are similar, these means are similar, but in correlation space, we'll see that it's actually effectively the opposite of that, that it looks a little bit more like a checkerboard here, that although these conditions 3 and 4 have similar means, they actually are very far apart in correlation space because the particular sequence of ups and downs doesn't match up. However, in contrast, if you look across the conditions that are sort of mismatched in the mean distance, so if you compare, for example, condition 1 to condition 3, these are actually quite similar to each other because although the means are far apart, they go up and down together across this sort of activity series, across this pattern. And so if we want to compare them all together in the same set of graphs, we can see here that the Euclidean distance is effectively a combination of the mean distance and the correlation distance. So the mean distance has this sort of blocky structure where conditions 3 and 4 and conditions 1 and 2 are similar to each other. And the correlation distance has this sort of checkerboard structure where you see similarities running sort of along the diagonals. Yeah?
And that's just the way this data was set up?
This is just the way that we chose to simulate this data. So normally, you wouldn't necessarily see these things pulling apart so cleanly here. But it's useful in this case because when we put them together, effectively combining mean distance and Euclidean distance, or mean distance and correlation distance, you can see that Euclidean distance is a combination of the two. So effectively, Euclidean distance is sensitive both to the mean differences between conditions that you would see in a normal univariate contrast, but also to the ups and downs of the pattern within that. So whether particular voxels, for example, in fMRI data, are more or less active, relatively speaking, ignoring the overall mean of the ROI, if you want to put it again in fMRI terms. So the most popular distance metric used in fMRI is the correlation distance, and one of the reasons for that is because it sort of explicitly removes the mean signal from the pattern. So ostensibly, what you're modeling in RSA is the distributed pattern of neural activity and how similar those are to each other, rather than just differences in overall univariate activity between different conditions. It's not, unfortunately, quite as simple as that because you're never going to perfectly capture sort of the region that you're interested in. So your ROI, for example, is never going to perfectly line up with the brain activity you're trying to model. And because the signal that you're looking at is effectively aliased, so like there's a partial overlap between the two, correlation distance still can pick up on univariate differences a lot of the time. However, it's much less likely to be driven by that than Euclidean distance, which of course explicitly takes both of them into account. Yeah?
Doesn't that assume that there's no information in the mean difference between conditions?
I don't think the argument is that there is no information. I think the argument is that people want to take that information out. They want to just talk about the distributed pattern information. So in the early days, people really want to make this strong argument about this isn't univariate, this is multivariate, this is distributed pattern information. And so they could see the mean as like contaminating that sort of distributed pattern effectively. So people wanted to remove that effectively. It turns out, because of the reason I was talking about the aliasing, it actually doesn't really matter as much. So there's some really nice simulation work by, I think, Russ Poldrak's group, looking at whether they measured the same thing, and they often do measure the same thing. There's slight differences in the types of variance that they tend to emphasize. Yeah, exactly. Yeah, and Alex was making the same point when he gave his talk, that you can formalize them mathematically to show that they're sort of essentially equivalent. The main difference, I think, is, well, there are a number of differences, which I'll get into later, between GLMs and RSA, but one of the main ones is that there's sort of an additional parameter in RSA, which is like what voxels you're including. The contrast will include all the voxels and not really consider how they're combined, whereas RSA, it matters a lot like how you define your region or network of regions or what have you. Their features.
There is a difference, however, between univariate and multivariate patterns. Mary Malley, she's a Colombian now, she's with Princeton. She has a toolbox called MUD, multivariate, univariate, I forgot what D is. Oh, thanks. So there you can take a look at, if you have in your fMRI data, you can correlate and see how much you get the same thing out of the univariate and multivariate. And in cases where you don't, then that's where you get the actual multivariate pattern as opposed to. And there are specific things, if you sit around and play with a bunch of matrices and try them out, there are specific ways that you can make multivariate patterns that you can capture with univariate, but there are some of them that you can't. So it's interesting to compare. And also with correlations, if you just add means to everything, correlations are not going to change. But still the underlying correlation of the time signal has to sort of be there nonetheless.
Yeah, so it depends on what multivariate measure you're using. In RSA, that's just correlation. If you did something fancier, like a support vector machine to classify some, yeah, exactly.
Or even logistic regression.
Yeah, I think it's a better argument when it's like a nonlinear thing that it's different, but.
I disagree. I use linear SVMs, linear kernels.
Yeah, but it's still an SVM, which is not just like a linear, like a purely linear model.
Well, I mean, logistic regressions have sigmoids.
Yeah, in that sense, yes.
Okay,
Yeah.
Logistic regressions.
Yeah, I just meant in terms of like linear, like ordinary linear regression. Yeah. Yeah, so once you have a similarity matrix, then the question is, how do you model this in terms of some set of features that encode some hypothesis that you have about your data? And that's what we'll talk about next, taking it sort of step by step, actually doing representational similarity analysis. And what we're going to look at here is the data which I talked about earlier during my sort of substantive talk this morning. So within the network of brain regions you see here, we're going to sort of extract the extended pattern from all of these voxels and calculate the similarity between the 60 famous people that participants thought about in the fMRI experiment I described to you before. And we want to see how can we explain which target people are viewed as more or less similar by the brain. So when we do this, we load in the data here. It's 1770 by 29 matrix. So 29 is the number of participants in that study. The 1770, this is the lower triangle of the correlation matrix. The reason we use only the lower triangle is that contains all of the meaningful non-redundant information. So the diagonal of a correlation matrix is always going to be 1, so you never want to use that because it's sort of constrained to be 1s, and so it's not actually informative about your data in any particular way. And the upper triangular element is perfectly redundant with the lower triangular element, so you only really want to model one of the two of them, or else it's sort of pointless. And we're going to start here just by combining the data from individual participants into a single neural similarity matrix. This isn't how it actually was analyzed in the data set, but what we're going to do is just combine it so we have one neural similarity matrix that we can relate to one prediction matrix. We're also going to read in one other piece of data, which is a bunch of ratings of all these celebrities on the psychological dimensions that I mentioned to you earlier. So these dimensions down here, things like warmth and trustworthiness and agreeableness and so forth. And a bunch of MTurkers told us where each of these particular people placed on each of these different dimensions. So a little bit later, we'll be modeling the data in terms of these instead of the similarity ratings. So here is our first RSA. It's a pretty simple command in R, and as I imagine it would be in most languages. It's basically just taking the neural similarity matrix, here encoded in NSIM, and correlating that with the explicit similarity matrix. These are judgments of pairwise similarity between these target people from a group of Turkers, and correlating these two things together. And we see that we get a correlation coefficient of about 0.4. And if we want to look at the scatter plot, you can see what this relationship looks like right here. So this would suggest that there's a pretty robust relationship between how people rate individuals as being similar to each other and how similarly their brains actually represent those individuals when we make social inferences about them, which is comforting. This is, I think, what we'd expect. It's not very informative about what they're using to make those similarity judgments at this point, but it's sort of a basic measure of whether there's some correspondence between brain and behavior. Yeah.
A little bit. So when Krieger originally wrote about RSA, he talks about dissimilarity matrices.
Mm-hmm.
I feel like most of us have now been like, forget it, like we're using similarity matrices. But could you just maybe comment a little bit about how you think about those, or like what if they make different predictions in the data?
Yeah, they're just like the flip sign of each other. There's really not any difference between those two. I often just talk about similarity matrices because it's an extra syllable to use dissimilarity matrices. It's useful in some sense to talk about dissimilarity because most or a lot of measures are measures of distance and dissimilarity are effectively the same thing in most cases. But mathematically, there's no difference. It's just a sign flip. Yeah.
It's important that if you want to decode things from each other, you're relying on them being neurally dissimilar. Mm-hmm. And if they're confused, then they're neurally similar. So basically in the sort of figuring out distinguishing things from each other, dissimilarity means they're decodable, but then similarity means they're confusable. So in that sense, when you're coming from that part where they wanted to distinguish neural sort of patterns for different objects, dissimilarity makes sense, which means I can decode them, they look different. But here, look, they're confused. So similarity is basically confusion, but changes in similarity matters, or correspondence of similarity to something else matters. So it's a different use than Krieger scored, I guess.
Well, yeah, I mean, I think they had a very particular perspective because they were related to, they were related to like the earlier decoding. Yeah, exactly. Any other questions I can answer at this point? Okay. Yeah, so one thing I'll mention in passing is that Krieger scored also recommends using the Spearman correlation coefficient to calculate the similarity between similarity matrices to calculate the RSA correlation. You can see that at the top line on the screen right now. Basically, just change the method to Spearman. Spearman is, of course, a rank correlation coefficient. So you just turn the metric variable you have into ranks. So the most similar, the second most similar, and so forth, and then correlate those things to each other. I think the reason that they gave for doing that in the original paper is like reasonable, that there can be big scale differences between different similarity metrics. However, in practice, I personally have not seen it ever make a very substantive difference depending on which correlation coefficient you can use. And in fact, in Roger Shepard's like 78 paper on like the psychology of similarity, there's a nice mathematical proof. It's like a simulation-based proof, but demonstrating that as the size of your similarity matrix increases, the rank similarity matrix converges on the metric similarity matrix. So the difference between them gets vanishingly small if you have a big enough similarity matrix anyway.
Spearman would be most useful when you don't have a normal distribution. So as the size increases, the more likely you are to have more normal. So if you have less, Spearman still theoretically should make more sense because it doesn't assume.
Yeah, so I mean, in some sense, Spearman has fewer assumptions.
Exactly.
Yeah,
Especially when we don't have a lot of data, it seems like theoretically Spearman
Right.
For some data sets.
Yeah, exactly. Yeah. Yeah, so then the question becomes, and this is related to the question of assumptions, is how do we test whether this correlation is significant, statistically meaningful, right? One way that you could naively think about doing this is just switching functions from core to core.test and getting the p-value out from your sort of parametric test of the correlation between these two things. This is actually not a good idea, and the reason is because the estimates in a similarity matrix are not independent of one another. So a particular similarity estimate depends on two patterns, so sort of the row pattern and the column pattern. And as a result, when you do a correlation test, it thinks you have 1,770, in this case, minus degrees of freedom, observations, independent observations. And so when it's calculating the p-value, it's actually being sort of very optimistic because it thinks you have all these like independent things, when in fact you only have, in this case, 60 independent things, the famous people. And so this p-value of this is just what R uses to represent 0 in machine precision for p-values. This is how accurate it can get with floating point, I guess. Is not really kosher, not really what you should be using here. So the more appropriate test is something which actually has existed for a lot longer than representational similarity analysis. It comes from the ecology literature, in fact, when they wanted to calculate distances between animals and relate those to each other. And this is the Mantle Test. And it's basically done by permuting the data at the level of the independent observation. This is what we're doing in this block of code. Again, if you don't care about R, you don't necessarily need to care about the syntax here. But what we're doing effectively is we're taking our lower triangular similarity matrix, we're turning it back into a square. We don't care what's on the diagonal. And then we're permuting the rows and columns in the same way. So if row 1 was at the top and row 3 was 3 down, we might switch those with each other, and we'd also switch the first and third columns of that same matrix at the same time. And so we'd randomize all of the order of the rows and columns, and we'd have a new similarity matrix that preserves the structure of a similarity matrix. It just happens to be in a different order. And what we can then do is recalculate the RSA correlation between the unpermuted model matrix that we have, that's just the similarity ratings that people gave us, and do this over and over again to get a bunch of permuted values to form a null distribution we can compare to the actual RSA correlation. So what that looks like, you can see actually just a little bit further down below here. So here we have what the correlation between the randomized neural similarity matrix and the original rating matrix looks like across, I can't remember how many samples I did here, but like 1,000 or something like that, permutations. And you can then see the actual value that we observed. This is the true correlation between the unpermuted similarity matrices. And you can see that this is wildly beyond anything we observe due to chance and permutations. So again, we end up with effectively a p-value of 0 to within machine precision. In this case, machine precision being constrained by how many permutations I'm willing to wait for. So this is a much more appropriate way of calculating statistical significance on similarity matrices. However, in most cases, you don't just have two similarity matrices that you're combining together. Usually, you'll have one similarity matrix for each of your participants in your imaging study, and you want to compare each of those to maybe the same or maybe different model similarity matrices. And when you have multiple participants, you can do this in an even simpler way, which is effectively just to calculate the each participant's similarity matrix correlation. So this NDAT is the 1770 by 29 matrix that we looked at earlier. So this is similarity elements, cells of the similarity matrix by participant. And by correlating this with the explicit similarity ratings, we end up with a vector instead of a single number. So whereas before we had 0.4 as our one correlation between brain and behavior, here we have a correlation from each individual participant's brain to the behavioral similarity matrix. So we end up with this vector, in this case of 29 correlation coefficients, one for each imaging participant. That measures how well that particular imaging participant was modeled by this particular similarity matrix. And to assess the correlation of this is a lot easier because now we have multiple independent measures. The independent unit here, instead of being the target person, is the participant in the study. And we can just do a t-test across them. You can see that I have a tan h in here. So this is the inverse hyperbolic arctangent. It's a trigonomic function. It also happens to be exactly the same as Fisher's z transformation. Fisher's z transformation takes R values, correlation values, and transforms them into values on the standard normal distribution, z values, that is. And we do that because correlation values are non-normal and non-linear. And so if you have, for example, the difference between a correlation of 0.1 and 0.2 is much different than the difference in the correlation between 0.8 and 0.9. That latter difference is like enormous compared to the former one. And so we want to stretch it out into a linear space using this Fisher transformation so that the assumptions of the t-test are valid. And then we just have a parametric t-test giving us the p-value here. Yeah? Yes. So this is effectively equivalent to a summary statistic approach to random effects, which is what we do most of the time when we're doing like statistical parametric mappings in whole brain analyses. So it has at least some promise that it generalizes across participants, like you can make an inference to the population of participants. If you average across all the participants first and then do the former analysis that I showed you with the permutation of the similarity matrix, that's effectively equivalent to an item analysis in sort of the common lingo, that basically that then generalizes to the level of different famous people in this case, but not to different samples of participants necessarily. Oh, you mean with the the Fisher-Z transformation? And again, in practice, I've rarely seen a difference between the two of them. However, I'd be particularly wary of a situation in which you see a lot of high correlations in your similarity matrix. Like if you have a lot of very correlated patterns, it probably will make a difference. But if you see a lot of patterns that just aren't very correlated, then it won't have much of a difference because the transformation is sort of nonlinear in its impact to linearize the correlations. So if you have correlations in the the 0 to like 0.3 range, they'll change like a very tiny amount. It won't be noticeable. Yeah, so that's another approach to calculating statistical significance. Of course, you don't need to rely on a parametric test either. You can bootstrap instead. So we have 29 correlation coefficients. We can simply draw repeated samples with replacement from those 29 to generate a bootstrap distribution around our mean correlation coefficient. In this case, you don't actually need to worry about the Fisher-Z transformation because the bootstrap doesn't care about the normality of the data. And you can end up with a nice confidence interval around your mean, which you can then compare to 0 or to another model if you have a standard for comparison. Here we see, just comparing this to 0, that we're outperforming chance pretty convincingly again in this data. And of course, if you look at each individual participant, it's probably a case where we don't really need to do statistics in some sense, because all except for one of these participants actually has a positive correlation between their neural data and the rated similarity matrix. So it's fairly obvious that something's happening here. Any questions about that? Yeah, again, a note I'll make in passing, you can sort of read up at the top paragraph here, is that really we should be controlling for item effects. This is not just true of RSA, but of like just general GLM models. We very rarely do control for item effects. This is less than ideal, as Tagliarconi and company pointed out, using some actual models. The problem with models that include all of the sort of maximal effect structure that you should include when you're modeling these things is that they tend not to converge ever, or take an extremely long time to converge if they're Bayesian models and they sort of are more likely to converge. So we're left in a situation where we often don't have sort of fully appropriate p-values that generalize both to different samples of items and to different samples of participants. And that's less than ideal. So one approach would be to switch over to using Bayesian statistics to estimate your mixed effects models. It's a lot more tractable to do that with just a representational similarity matrix than with the entire GLM of a whole study. The other alternative, which I'll actually talk about a bit later on, is cross-validation. So you don't need to necessarily rely on a hypothetical promise of generalization to new items guaranteed by parametric statistics. You can actually directly test the generalization of new items if you train a model on certain items and then test it on other items. So that can be another way around this particular issue. So the next thing I'll talk about briefly here are effect sizes. So how do we tell beyond a p-value, which just sort of gives you information relative to null distribution, how can you tell whether effects are big or not? And the easiest way to do this is actually just to look at the correlation coefficient if you're doing the item analysis level RSA. So here we can see a correlation of 0.4. That's a pretty big correlation by the standards of social psychology, probably smaller by standards of other fields. My parents work in wine science, and when I get an R squared less than 0.95, they're really disappointed, so standards vary. But in my opinion, this is like pretty big effect size right here for the type of effects that I usually see in my data. However, it's also probably a bit smaller than it ought to be. And the reason for that is that we don't perfectly measure the thing that we're trying to measure. The neural pattern similarity varies across people. Some of that might be like real idiosyncratic differences between participants, but some of that is almost certainly just noise that we just didn't perfectly measure the underlying bold signal across the course of the experiment. And one thing we can do here is we can calculate how reliable our neural signal is. So here I'm just using the alpha function to calculate Cronbach's alpha, which for those of you who have any psychometric background will know that this is just a measure of the reliability of, usually used for surveys. You can use it across participants too. They're a measure of the sort of reliability of the average across participants. So this cross-participant average encoded in NSIM has a reliability that's equal to 0.5, which is not great. That's probably because there's quite a bit of difference between different people. People have different impressions of these famous individuals. For example, this study was actually run a few years ago, well before the 2016 election, but people like Vladimir Putin were in this list. And I imagine that particularly if we ran that like right around election time, there would have been massive polarization between any participants we had who happened to be conservative versus participants who happened to be liberal. And so there's real like variance that's causing this not to be perfectly reliable, not just sort of noise, but for the purpose of this item analysis and that correlation of 0.3999 or whatever, we're perhaps underestimating how much of the true or the sort of explainable, possibly explainable variance we're actually explaining. And so what we can do is we can actually disattenuate the correlation. So this is a really old idea going back to Spearman in a 1904 paper. You can basically take the correlation between two measures and divide them by the square root of the products of their reliabilities. And this will give you the true correlation in a situation where you measured both of them without any measurement error. And so you can see that dividing 0.4 by the square root of 0.5 gives you 0.56, so a larger effect size there. So this is probably a more accurate estimate of the relationship between these two things, assuming we sort of measured an infinite amount of data to get that really high reliability. The fact that we're just dividing by the square root of the neural data's reliability here basically just assumes that we measured the other the ratings with perfect reliability, which isn't very realistic, of course. I just did not want to go through and calculate the reliability of the rating data because that's buried somewhere very deep. The individual subject data that I need for that. However, you could also disattenuate for that as well. And we'll come back to the idea of disattenuation in a little bit when we talk about cross-validation, because disattenuation is inherently very closely tied to the idea of a noise ceiling. They're effectively just different formulations of the same concept. Noise ceilings are a bit more popular in neuroscience, and I think probably rightly so, because they give a reference point without sort of hiding the reference point from you. But they are conceptually, mathematically, effectively the same thing. You can also calculate group level effect sizes. And this is another way of estimating what's going on, how substantive the effect is in your data. So this is now across participants. You can see how large the mean is relative to 0, and divide that by the standard deviation across participants. Again, we're using the Fisher-Z transformation here to normalize these data. And what we can see is a Cohen's d of 2.1. So according to the old rules of thumb, 0.8 is a large effect size. So this is like a little bit more than twice a large effect size. So it's like a huge effect that like similarity predicts, rating similarity predicts neural similarity. Great, like not terribly surprising, but somewhat comforting, I suppose. Next, I'm going to talk a bit about cross-validation. So we have multiple measures of similarity. We've already talked about the two you can see on the screen there, the neural similarity between these famous people and the explicit ratings. But we also have another measure of similarity. This is how similar their Wikipedia biographies are to each other. So we scraped all the biographies of the 60 famous people from Wikipedia, and we just did a bag of words approach because word embedding things weren't really that popular back then. And we compared how similar the frequencies of the different content words are to each other. And what we can see here is that the text is actually also positively related to both the explicit ratings, so that's a correlation about 0.5 there, and to the neural similarity ratings, or neural similarity estimates from the fMRI data. So one could ask a question about how well can a model that combines both of these predictors account for the brain activity, the neural similarity between these famous people. And one way we can assess that is through cross-validation. So what we're doing here is effectively we are fitting a model. We're choosing coefficients for rated similarity in text by fitting the model on all of the participants except for one. And then we're testing those coefficients in that model by predicting the neural similarity in the one left out participant. So this way we get an unbiased estimate of sort of how well we can explain that one left out person. Now, we'll leave one out cross-validation, not necessarily the best mode here, but it's a fairly simple approach. And it works well with noise ceiling, which I'll get to in a moment. The one sort of special feature here is that we're fitting this regression using non-negative least squares. This is something that Kriegescourt and company have advocated for. It embodies a certain assumption about the data, that effectively all the data should be positive, which makes sense if you're thinking about distances. There's no such thing as a negative distance. And then it also expects all the coefficients to be positive. So there should be a positive relationship between your distances, your model distances, and your brain distances. And that's a more substantive assumption. There could be like real meaningful, interesting negative correlations between neural similarity and another similarity measure you want to test. But in general, I think most of the time we expect positive correlations. You should just be wary if you do have a prediction about a negative correlation. Negative correlation is a little bit weirder to interpret, but it basically just means that the further apart things are on some feature, the more similar they are in the brain. So a good example of that is in social psychology research, the cross-race effect, where target people who are of the same race are viewed as more similar to, as more different to each other if they're within your own racial category, and more similar to each other if they're in another racial category. So that would actually potentially elicit a negative correlation with this neural similarity measure. So we get this correlation here, which is just the mean cross-validity performance predicting neural similarity with these two things. And we can also assess this using other metrics. So you could do things like RMSE or any sort of error measure. However, now we're left with a similar question to what we were before. Is we have this correlation of 0.11. That seems like not a very great correlation. But how well could we have done? And we can assess that using a noise ceiling. What the noise ceiling is basically the same prediction without a model. What I mean by that is we simply take the average of all of the other participants' similarity matrices, and we correlate that with the one left out person's similarity matrix. And we do this iteratively, leaving out each participant in turn. So we get essentially a correlation between all but one and one, leaving out each participant one at a time. And then we simply take an average of those correlations to estimate what's called a noise ceiling. So this is effectively how well we possibly could have done using the perfect model, which is just other people's data. So given the reliability of other people's data and other participants' data, how well can we model this one left out participant's data? Now again, this sort of this has an assumption that was popular in the early RSA days because it was mostly with vision, and vision is thought to not have too many individual differences compared to, say, social cognition. This is a little bit unrealistic in social cognition because there probably are like really substantive individual differences here. However, nonetheless, what we can do is we can effectively disattenuate the correlation simply by dividing the actual cross-validated performance by the mean of this, this noise performance. We can see that we're achieving performance at about 86% of the noise ceiling. So we're doing, better than 80% as well as we could have hoped to have done, given how well the data from one participant maps onto the data from all the other participants. Yeah.
Do you have an intuition or preference for when you might do that versus when you're doing your iterative non-negative least squares to just generate a null distribution by permuting the model and then comparing your out-of-sample accuracy to that null distribution rather than, so let's say you're doing 85% of the noise ceiling, but that's well within the range of what crap models do anyway.
Yeah, so those are different questions. One of them is a question about could I expect to see this due to chance? Right. And one is how well am I doing correcting for the amount of noise in the data? Yeah. So I think you need to do both, pretty much.
Have you ever encountered a situation where you actually find that even though you look like you're doing a good job, you're just well within the range?
Yeah, so that's one of the things, that's one of the reasons why people have traditionally criticized correlation disattenuation measures, is that when you are doing very badly, you can end up in a situation where not only are you doing well, you can actually be doing better than your noise ceiling if you have a poor estimate of your noise ceiling because you have bad data. And it's just not very reliable. So you can actually end up in situations like, I'm doing 120% as well as the noise ceiling. I'm really doing great. That's not very realistic, but that'll happen a lot if you have data which falls within the permutation distribution of the null. Yeah. Yeah, so you really shouldn't probably do this at all until you've seen if this is a significant result. Thinking about time here. So this is what I was describing to you earlier, this issue that we have a little bit of a problem with our traditional statistical testing methods because we rarely account for the items, for the stimuli that we're showing to participants. We usually only model random effects of the participants. So we allow participants to be different from each other. We don't allow the stimuli that we're looking at to be different from each other. And this effectively means that we can't necessarily make inferences to other populations of stimuli. In this case, the conclusions sort of generalize to other participants who see these same set of famous people, but not necessarily other sets of famous people. And that's an inference we'd really like to be able to make, right? So one way you can get at this without having to fit these really difficult mixed effects models that maybe won't ever converge is through sort of tricks of cross-validation. If you can cross-validate across a particular boundary that you're interested in, you can get an idea for how much things actually generalize across that. So in this case, we're doing a little bit of twist on the cross-validation that I described to you before. So instead of cross-validating using all of the data from all of the participants except for one, we're using all the data from all the participants except for one, except we're actually just cutting it in half. We're using data from half of the famous targets, as well as just all the participants except for one. And what that means effectively is that now we're going to cross-validate from you thinking about 30 famous people to you thinking about a different set of 30 famous people. If the model still performs well, that's a good indication that this actually will generalize across different sets of items, even though we're not doing the formal statistical testing procedure that would be involved in mixed effects modeling. And what we can see when we do this in this particular data set, at least, is that you end up with performance which is, sorry, yes, you had a question.
Sorry, if I remember your talk correctly from earlier, I thought what you were saying was that every participant didn't see each of the 60 people, but that you sparsely sampled 60 people across subjects. Am I misremembering?
I probably misspoke, but, okay. but yeah, no. Every participant saw all 60 of these famous people. They saw, in the mental state study, I think the difference might be in the mental state study, they saw different sets of scenarios paired with each mental state. But
I guess really my question is, like,
yeah.
To do this stimulus set splitting, does every person need to have seen the same stimulus set?
Not necessarily, no. So yeah, you can. Yeah, no, you don't. There needs to be some overlap. Actually, now that I think about it, I don't think there even needs to be overlap, as long as they're all represented on the same features. Yeah, there doesn't need to be overlap. So you could train a model, like let's say we had one set of participants, like let's say we had this sample where we had 60 participants, 29 participants look at these 60 famous people. And we had a subsequent study where we had another group of participants look at 60 new famous people. We could build a model just on this data set and test it on that new data set, even though there are no target people in common. What we're learning from the first data set are the weights on the different feature vectors. So in this case, the explicit and implicit similarity, textual similarity. So that's what's being generalized across them. So as long as we have the text associated with the biographies, and as long as we have the explicit ratings of similarity from the new group of people, we can generalize across that boundary, even without shared target people. Does that make sense? Okay. Yeah.
I think the confusion came from the fact that in the morning you said the sparsely sampled instances were from the trial, so the questions that people were seeing were not the same across individuals, right? Tasks like Bill Nye would do, like learn karate, yes or no.
Yeah. So yeah, I can see why this is confusing. Actually, in that particular experiment, people did see, it's like every participant saw the same full crossing. It was in different orders, but this full crossing of items and people. The items themselves, though, were chosen from a larger set using previous data to cover the space of possible inferences as widely as possible. Yeah. So yeah, what we can see here when we do this cross-validation with respect to both participants and items simultaneously is the performance drops a little bit, but it actually doesn't drop very much. It drops, a couple percent really. That's actually a really good sign, right? That suggests that the performance of the model is not reliant on the fact that we use this particular set of people. It generalizes to a new set that hasn't previously been seen before. So this kind of approach can be used to estimate generalization across any kind of boundary. So you might have, for example, multiple classes of items or conditions. You might cross, for example, these famous people with different mental states they could be thinking about or something like that, in which case you could generalize across both of those boundaries with an appropriate cross-validation regime to see how well your results generalize and be sure that you're not making a bad inference in that sense. The last topic I'll cover in this section is model selection. So you might have a big set of features, and you're interested in what combination of them allows you to best explain the similarity between neural patterns of brain activity. So in this particular case, we're going to take the big 5 personality traits that I mentioned to you earlier and see what combination of those 5 allows us to best predict the neural similarity data that we have. And there are different ways of doing this. In this particular instance, we're taking the leave one out cross-validation I described to you earlier and just cycling through that with different sets of these, so every possible set of the 5 different traits. So just considering extroversion, just considering agreeableness, and then every combination of 2 of them, every combination of 3 of them, every combination of 4, and the one combination of 5 of them. Now this is not a very efficient search approach, and it gets totally intractable if you have a certain number of dimensions. When we only have 5 of them, it's easy. If we had even as many as like 10 or 20, it would definitely become computationally challenging, and you'd have to think about other approaches to search through the space. You can do something like building up the model, basically effectively a forward greedy search. So you'd start with the best single predictor and then add in the next best predictor and add in the next best until you ran out of predictors that added anything to the model. But when you have a small number, you can just do this exhaustive search on all the possible models. And you can just see which of them provides the best cross-validated performance, which is what we're doing at the end here. We're looking through all of the different possible model performances and selecting the combination of trait dimensions which best predicts in this cross-validated regime the neural pattern similarity. And that happens to be conscientiousness, extroversion, and openness in this particular set. Now, one particular trick about this is that if we wanted to then evaluate the performance of this model, say, OK, we have the best model, how well is it doing? We wouldn't want to just look at the same data. And the reason for that is that you can overfit at the level of your parameters. You can sort of have the over-tuned regression coefficients. But you can also overfit at the level of model selection. You can look through so many possible combinations that just by chance you happen on one that predicts pretty well. And so even if I, for example, instead of feeding in real feature vectors here, fed in totally noise data, I'd still get some models that perform better and some that perform worse. In this case, I'm not searching through very many models, but if I was searching through a huge space of models, I could potentially find one that by chance does quite well. And so what you would want to do here is add a second level of cross-validation where you split your data in some respect, did this model selection procedure on half of it or on some subset of it, and then evaluated it on that left out set of data to get an unbiased, non-overfit estimate of how well that optimal model is doing. So just a sort of second layer there in case you want to be able to evaluate this, say, relative to a noise ceiling or something like that, as we've done before. And the last topic I'll cover quickly here is how to explore neural similarity. So most of the time RSA is talked about in terms of this confirmatory style of analysis where you have a model matrix that you're trying to fit, or a set of model matrices that you're trying to fit to some dependent neural similarity matrix. You can also do exploratory analyses, which are oftentimes really helpful, though. So you can do multidimensional scaling. This is perhaps the most popular one. This is an algorithm that basically takes in a distance matrix and tries to project all the points into an n-dimensional space where n is usually 2, because that's easy to look at, and do so in such a way that it preserves all the distances between the different points. So this is a really nice example to, I think, get the intuition. So this is an MDS generated by feeding into an MDS algorithm all the distances, airline distances between cities in France. And you can see what comes out of it is actually a really pretty good reconstruction of a map of France. Now, this also illustrates one drawback of MDS, which is that this is rotated. The north is not pointing up because the MDS doesn't know anything about north. It just knows about distances. So you can't necessarily take the axes of the MDS as being inherently meaningful. The meaningful axes, like north and south, might be at some angle with respect to the actual configuration plot. But this is really useful for being able to project this information down into 2D space. Things like hypertools, which Jeremy was talking about, have MDS as one of the ways of visualizing the data dynamically. So this is what our data looks like in a configuration plot. A little bit circular, a little bit circumplexy, reminiscent of certain theories of person perception. But you can see certain people are closer and further apart from each other based purely on how similar the patterns of brain activity they elicit are. Yeah?
Can you briefly just, based on what distance metric you provide the MDS, how does that change the sort of solutions you get?
I mean, it will have very different solutions depending on which one you feed in.
Is there like a canonical preference for what to give past MDS?
I mean, you can try different ones. This is an inherently exploratory technique, so it's worth just exploring and trying different ones to see if they reveal different aspects of structure. However, if you have particular confirmatory analyses in mind, either then or later, you should probably use whatever metric you're planning to use in that analysis. So if it's correlation distance that you're going to test with later or earlier or whatever, then use correlation distance. Yeah. Now, one good question you should ask about this is this actually a good representation of the data? So France is roughly two-dimensional, but it does sit on the surface of the Earth, which is not quite two-dimensional. It's a sphere. And so you could imagine if you had airline distances between cities that are even further apart in different countries, for example, a two-dimensional solution would no longer be a very good fit at all. You'd have to have a three-dimensional solution that would allow for the spherical configuration of cities on the surface of a globe. And so what we want to know here is, like, is this actually a flat map, or is this a globe, or is something even higher dimensional? Is this a reasonable representation of the data? And the key statistic to estimating that is what's called stress. So stress is a, oh, I don't have it printed out, do I? Rats. I edited this, and I think I cut out the actual stress value here. So the usual rule of thumb for stress is that it should be less than about 0.15 for a good fit. Unfortunately, it's not really a good rule of thumb like most rules of thumb, because stress will vary with the amount of objects that you're scaling, in this case, the number of people. So a scaling with 60 people is going to have different standards than a scaling with 20 target people, for example, if I did that instead. However, this has a pretty high stress. This stress is like 0.3, which is kind of garbage. And so this is not really a good representation of the data. And we really need a higher dimensional representation, which unfortunately doesn't make much sense either, because then you can't really visualize it very clearly unless you do like a three-dimensional rotating box like in hypertools. But one thing I'll illustrate before we go on from this is one thing you can do with MDS, which is really nice. This is sort of an embellished MDS. It's the same graph, though, is to put biplots onto it. So this can tell you how the axes of your graph relate to the dimensions of interest to you. You basically just correlate a particular dimension, like sociality or valence, with both axes of your plot, and then the direction of the vector and the length of the vector depend on that correlation. So for example, if this is correlated negative 0.4 and with the x-axis and positive 0.2 with the y-axis, you get this vector that goes in this direction. So it's a really nice way of sort of putting axes onto an MDS to let you interpret it a bit more easily. Oh, that's not printed out. In that case, I'll have to.
Shakespeare and Churchill were as powerful? Like, what was the notion of power?
So power was a name we gave to a principal component, so that's probably why it's not a very good fit. We just wanted to have a name that was discrete from the names of the original variables. Yeah, so it's a combination of things like competence perceptions, so that's going to be more domain specific and can account for some of this, and like conscientiousness as well.
Not influence, like.
We didn't measure that. I expect that would be, yeah. So I need to actually run some of this.
Is there a way to plot it where their relations maps onto their influence? Like their graph position actually expresses how influential somebody had been? Because they're celebrities themselves that people saw they were related to each other too.
Mm-hmm.
Some of them have influenced others.
Mm-hmm, mm-hmm.
So in a manner of speaking, they were observing the graph of relations. Although here it's more individual.
Right.
So I wonder whether there's any analysis that you did that would talk about the relation between the nodes.
Yeah, so I mean, I think, I mean, it's a little bit similar to some of Carolyn's work. They're not with famous people, obviously, but looking at sort of social network distance and how that correlates with neural similarity. So I can maybe let her talk to some of that when the time comes, or now, if you want to. So one useful approach when MDS fails, like we've just seen here, is instead to use TSNE. So this is a, basically you can think of this as a local nonlinear version of something like PCA or MDS. What it tries to preserve is the local relationships between the objects in your data. So MDS and PCA, they really care about the global structure. Are the big clusters in the same orientation relative to each other? But they don't really care about preserving the nearest neighbor structure. So if Cameron Diaz and Will Smith are actually nearest neighbors in the neural similarity data, PCA might not reproduce that, MDS might not reproduce that. TSNE will particularly try and reproduce that. It won't necessarily try and reproduce the global structure of the data. But you can see that this yields a very different sort of configuration plot. The one tricky thing to my mind about TSNE is that you have to choose a parameter called perplexity. That, yeah, is very perplexing, and that basically determines sort of how flat this is. So if you turn the perplexity way up, you'll end up with sort of a uniform tiling of the space, where each person is sort of equidistant to all of its nearest neighbors. If you turn it way down, you'll end up with these like really collapsed, sort of odd-looking clusters. And in the middle, there's informative stuff. And I think there's actually a really useful thing that I link. Yep, just here in the HTML. There's a fantastic like interactive visual explanation that you can play with perplexity and learn more about it if you want to use TSNE at that link. And the final exploratory tool which is really useful is hierarchical clustering. So I'm not going to go into the details of clustering because that's a whole other topic, but one thing you can do is basically feed this into a agglomerative clustering solution which tries to put likes together and sort of join people who are similar to each other. This also has a property that you don't need to worry about projecting it onto a space, which is really nice because that has so many constraints. And so you can get a really good sense for what the structure is in your data, how much of the variance is accounted for by like really sort of low-level dyadic similarities between pairs of people versus like big clusters of people and that sort of thing. So here you can see like a lot of structure in terms of like Vladimir Putin and Edward Snowden being like really close together, probably because Snowden went over to Russia very shortly before this imaging project was scanned. So this is another really useful technique, I think, for visualizing this data and trying to explore what's actually underlying the representational similarity you're trying to explain with your theories. The one other thing, which wasn't originally part of my tutorial, which I'll just talk about briefly here, is Kenny Loggins. Oops, that's reverse direction. Oh, OK, it was coming up. So Alex Huth made the point earlier that maybe RSA is dangerous. So welcome to the danger zone. I just wanted to add a couple comments to that. One question he raised is, does RSA assume equal weights on all features? That's true if you choose to combine all features into a single similarity matrix and then use that to correlate with your data. If you do mixed RSA, like we've seen in a couple examples here, we have multiple predictors in a regression, all predicting a similarity matrix, that's no longer an assumption of the model, so we don't need to actually worry about that issue. He also brought up a question about does RSA increasingly penalize models where the features correlate across voxels? This is an idea that, like, maybe I have two dimensions, warmth and competence, that are orthogonal to each other in terms of ratings of my participants, but they elicit similar patterns of brain activity when I sort of correlate them with neural activity. That is true. However, it's also slightly true of GLMs as well, just to a lesser extent. And also, I think it's actually arguably a feature rather than a bug, depending on what you want your models to do. This is effectively penalizing models for having a naturalistic correlation even when you've artificially separated them. So if you want your model to do that, which I think a lot of the time we do because we don't really know the naturalistic correlations between things, then this is actually kind of a nice feature to have. Another issue is, does RSA just generally underestimate effect sizes relative to GLMs? If you simulate data without any measurement error, then the answer is yes. And it's in fact yes for even more reasons than Alex went into. So if you want to check it out, I have a blog post about how there's an additional sort of square root underestimation of RSA correlations. But all that's in noise-free simulations. If you add measurement noise into your simulations, then actually RSA will most frequently have larger effect sizes than GLMs at the voxel-wise level because the GLM just considers each voxel separately. Whereas in RSA, you're combining across many, many voxels a lot of the time. And effectively, you're disattenuating a correlation by taking an average across voxels and getting more signal that way. The final thing I'll say before I turn over the floor to Ida is just there are some pros of RSA relative to GLMs. They're much more computationally efficient. Anybody who actually followed along with me today probably noticed that you could download the data in about half of a second. That contrasts a little bit with the difficulties we had getting some of Alex's data downloaded. So it's more portable. It's a little bit easier to work with. It's faster. No, I mean only turnabout's fair play. It's easier to make comparisons across modalities for this is why Krieger's court came up with this method in the first place, that it's easier to compare similarities across different measures and different metrics than to compare the measures with a direct comparison. There are less issues with rank deficiency, so you can a lot of the time use like traditional OLS correlations and things like that in cases where it'd be rank deficient otherwise, because you're basically taking, for example, 60 data objects and stretching them out into a 1700 by 70 similarity vector, so you get sort of a bunch of additional fake rank that helps things fit. It can yield some different insights to the GLM because of this additional parameter of which voxels you include in a particular searchlight or region. That if you happen to combine, say, region A with region B, you might get a very different idea of the neural pattern similarity they combine in region A with region C, even though they might all be adjacent to each other. And finally, one useful point that was again made by a paper by Russ Poldrak's group, which is that RSA sort of nicely, depending on your goals, suppresses between subject variance. So if you want to do individual differences, RSA is probably actually a bad choice. But if you want to maximize your power to do sort of just a standard group level analysis to see if an effect is present in a population, RSA is actually quite helpful there because it eliminates some of the big differences that come out of GLMs. Of course, Alex doesn't actually combine, he fits his data to each subject individually, so this is probably why it didn't come up when he was talking about that. Yeah, so anyway, there are some advantages to RSA. And with that, I will say thank you, and I'll turn over the floor to Ida. Any questions I can answer as we're changing over? Yeah. Yeah.
Have you looked at whether that resultant correlation matrix looks different based on whether you estimate a single GLM with all your things in it at the same time, or the Jeanette-Mumford style, you know, one versus all, and then iterate through them? You get a different. Maybe do a 5-minute just.
Yeah, so honestly, I haven't systematically compared that. Yeah, I think it would matter the most in situations where you don't have great orthogonalization between your conditions. If you have enough data that those are like really pulled apart, then I don't think it should matter too much. But if there are some incidental correlations, then it probably will matter more.